All right, welcome to Mr. Joyner's chemistry class. We're going to start with this warm-up, so remember, write the question and the answer. Your two questions are here. What can you infer from this picture, and what would be a bad inference from this picture? And then you will turn your warm-ups into the substitute, and she will go ahead and keep those for me. Remember to give her not only today's warm-up, but yesterday's, because we turn our warm-ups in on Fridays. So let's talk about what an inference is first. It refers to the process of using observation and background knowledge to determine a conclusion that makes sense. Basic inference examples can help you better understand this concept. So that's what we're using this warm-up for, to infer something. Like, let's say you see something that's shaped like a triangle, and it's upside down, and it's red, and it has white lines around it, and all you can see is the letter Y in there. You might infer that that was a yield sign, even though it didn't finish the words out to say yield, because of your past experiences with coming across yield signs that have the complete word yield. So from this picture, what can you conclude? Pause here and write down your answers. Okay, once the warm-ups have been taken up, the substitute teacher will pass out all of your note-taking guides for this particular recording. So pause here for that. So what is science? The goal of any science is to investigate and understand the natural world around you. And that's what I love so much about it, is there's so many things to have questions about and be curious about. And you want an explanation for why is the sky blue, or why does this work that way, or how do plants grow, and all these other things. And then you want to make useful predictions like, hey, is a tornado coming my way? Or what will the temperature be like tomorrow? You want those kind of things, and that's what science is all about. It can be descriptive. It can be comparative. Like, is this fertilizer better than that fertilizer? Or it can even be experimental. So why is science important? Well, an old proverb says, it is the glory of God to conceal a thing, but the honor of kings to search out a matter. It's not just good enough to say, well, that's just the way it is, and leave it at that. We need to probe it and figure it out, and find out all the wonders that are locked in on that. Also, you want to be an informed person that won't be easily tricked by some advertisement, or easily tricked by some claim out there. And there's plenty of those out there. If you do enough science and do your own experiments, you can find out if what they're saying is really true, or if what they're saying is even worth experimenting, because there's no way it can be true. To make useful predictions also, and explanations, and develop things, technologies come from science. And I want you to think like a scientist. I want all this to, what we learn here, to rub off on you, and you become someone who can think critically, and someone who looks at a problem and knows how to solve it and break it down, and do those experiments that are going to create valuable information. But a scientist thinks like this. First, he knows, or she knows, that they must identify a frame of reference. So if I am out there in space looking at you sitting in your seat right now, from my point of view, you're rotating around the Earth at so many miles per hour, so you're going pretty fast. But from your point of view, you're just sitting still. So frame of reference is pretty important. Determining initial conditions. So were you in that seat before? Or had you arrived there after the bell rung? Or was that substance already hot before you started this chemical reaction, or did it heat up because of the chemical reaction? Note what occurs when, where, and in what order. Note final conditions and make interpretations lightly. Don't just use that one experiment to make a generalization unless you're ready to do experiments to verify that generalization. And then test your interpretations. And that's the beautiful thing about science is it's ongoing. It's falsifiable. It's testable. Otherwise, it's not science. So can science explain supernatural phenomenon? No, because it's not falsifiable, it's not repeatable, it's not testable. So there are limitations to science. And when you are doing science, you need to take data, and there are two main categories of data. There's quantitative, think quantity, numbers, and and the other one is qualitative. I think quality. Quantitative data deals with numbers and things you can measure. So for instance, I can line you up from shortest to tallest, and I can get a ruler and measure, and then I can write down those measurements. That would be quantitative. But take that same experiment where I list you from shortest to tallest, and I just say these people are short and this group over here is tall. Well, that would be qualitative because it's more descriptive. Like, for instance, you say with this fertilizer, plants grow more. Well, that's descriptive. That would be qualitative. But if I said it grew by this much more each day, well, that would be quantitative. And going back to inferences, here's my sign that is this shape without any words. Can you infer what type of sign this is? I hope you said stop sign, even if it's in a completely different language, because it's in a different country. Usually, this shape will mean a stop sign, and you can base that on prior knowledge because you've seen this sign before and know what it means. After initial observation, scientists will propose a hypothesis. So you notice something going on around you, become curious about it, and you form a hypothesis. In other words, you're trying to give an explanation why that's working that way based on your prior observations. And when you come up with that hypothesis, then that hypothesis can be tested. If it's not testable, it's not really a hypothesis, or at least it's not science, and so therefore you're not even starting with a hypothesis. When you are testing it, you need to make sure that you're testing what it is you're testing and that there's no other variables that are influencing it. So you want to control as much of that environment as possible. And then you continue to gather more data even after that experiment. And then science is ongoing, like I was mentioning, with the continue to gather data. Just because it may be true now may not be true in the light of new advances. For instance, they would say that sicknesses came from spirits. But with the advance of microscopes, we can now see a lot of sicknesses come from bacteria and viruses that we couldn't have solved before, so we wouldn't have known that. Good scientists question both existing and new hypotheses. So hypothesis is not set in stone. It's always good to look at people who are out there trying to question these existing hypotheses, sort of like Snopes here. You can go on to Snopes and ask the question, hey, is this article I saw really true, to verify it? Or you can go to people like this, Captain Disillusion, where he looks at these popular YouTube videos and says whether they were how you can spot whether they are trick photography or not, or how they went about making these things, or did it legitimately happen. And he's an expert on media, so he knows all the tricks of the trade. In Snopes, if you, for instance, there was one time that everyone thought that Bill Nye the Science Guy died from some vinegar and baking soda experiment because he'd stopped showing up on TV. He went, and the reason why, when you look into Snopes, is because he went into public speaking. Since then, he's returned back to the public media and videos and shows, but not under the same kind of entertainment. New knowledge gained through scientific research has scientists continually revising and reevaluating their ideas. Like I mentioned with the microscope or telescope or any new advanced technology, you're going to find out new things. Many scientists today contribute to the ideas we once had of health and disease and further our knowledge so we can treat these things better and realize the relationships between these things, relationships between the living and non-living parts of the environment. Understanding science and scientific approach is essential to making informed decisions about major issues. When you do it, you need to do science. You need to understand what the social norms are, what was moral and what is ethical and what is legal. Okay? Just because you want to find a cure to disease doesn't mean that you should go about making a bunch of people sick and doing experiments on them. That would not be moral or ethical. Designing an experiment, you want to design it to answer the question that you were asking, and therefore it has to be testable. And then you, of course, want to form a hypothesis about how your experiment you think is going to turn out. You never say, I think in a hypothesis. You always say, this is going to happen. If this is what I do, then this is what is going to happen. And you base that on inferences on prior knowledge. So you want to start off by setting a controlled experiment so that you are only testing one variable at a time. One variable is changed at a time and all others then will remain unchanged. And that's why it's called a controlled experiment. The variable that is deliberately changed, that you are deliberately changing, is called the manipulated variable. So for instance, if I'm trying to see which fertilizer makes plants grow better, the variable that I'm manipulating is the types of fertilizers I'm using. The variable that is observed and changed is called the responding variable. So if you're trying to find out which fertilizer is best, the thing that's going to change is the height of the plants, how they're growing. So that would be the responding variable. Then you, of course, already want to have it set up in your pre-lab writing, a data table for recording and analyzing. You want to make sure you're doing it with accuracy. You want to make sure you're doing it with precision if you have other people also doing the experiment. You must be willing to accept that your hypothesis gets refuted in the experiment or that your experiment gets supported. It winds up supporting your hypothesis. You want to have any biases. Just because you think an experiment should turn out a certain way doesn't mean you can manipulate the data to fit your ideas. And make sure that it doesn't have any errors. If you notice that there are some, you need to note those and not come to any illogical conclusions. Speaking of which, draw a conclusion, and then when you do, that's communicating and reporting it. And there are various different ways you can conclude those and report those. Then you want to be able to publish those, put those into your lab notebook, or put those into an article. Many scientists don't get the Nobel Prize, even though they're the ones that first did the experiment, because they didn't publish it. And then when it is published, whatever you're publishing needs to be reproducible. Like you give steps that are detailed enough for someone else to follow. That brings me to another thing, the difference between hypothesis, theory, and laws. Laws do not make an explanation, just an observation. Like, let's say things fall on Earth at 9.8 meters per second per second. And we continue to test that and test that and test that and test that. And that's what we've observed to always happen. We're not making an explanation of why they're falling at that speed, just stating it. That would be a law. Now, if I try to explain why they fall at that, that becomes a hypothesis. And then a hypothesis, if it's tested again and again and again and verified, then that can graduate to a theory. Theories have undergone many, many testing. That's the only difference between a hypothesis and a theory. No theory is really an absolute truth. So that's the big difference between a law and a theory. And that concludes our presentation.